Welcome to the wonderful world of astronomy. This is chapter 14 on the sun, and part 2 of chapter 14 is energy, from the core to the surface. I want you to remember from chapter 7 some things that you learned about the sun. First of all, that the sun contains more than 99.9% of the solar system's mass. So by far, of all the objects in the solar system, the sun is by far the largest, the most massive, the most dominant thing in the solar system. It's composed 98% of hydrogen and helium plasma. Remember, plasma is like a gas, but it's been ionized. So you have hydrogen nuclei, which is pretty much just protons, and helium nuclei, and then electrons. And that 98% is mostly hydrogen. In fact, it breaks down to about 73% hydrogen and 25% helium. Every second that goes by, the sun transforms 600 million tons of hydrogen into helium, but only 596 million tons of helium. So every second that goes by, 600 million tons becomes 596 million tons. It loses 4 million tons. And that's because by Einstein's famous equation, E equals mc squared, that mass, that 4 million tons every second gets converted into energy. So it gives a lot of energy. By the way, thinking about the size of the sun, here is part of the sun and a solar prominence. You'll learn about these later. And approximate size of the Earth relative to that prominence that's shooting out in the sun as a whole. We're going to start by looking at nuclear fusion in the sun. Our goals for learning: how does nuclear fusion occur in the sun? How does the energy from fusion get out of the sun? And how do we know what is happening inside the sun? We'll first look at how does nuclear fusion occur in the sun. In chapter 5, you learn that two particles of like electrical charges repel each other. So remember, opposites attract and like charges repel. In the picture above, you can see two protons. If they are coming at each other, they will repel each other. They will want to turn around and go in opposite directions. But nuclear fusion is a process wherein they actually come together and fuse together. So what this means, if like charges repel each other, then two positively charged particles like protons will repel. Also, two negatively charged particles like electrons will repel. There are two types of nuclear processes, fission and fusion. Let's look over on the left. Fission is the process wherein a large nucleus splits up into smaller nuclei. And this is used in nuclear power plants, where they use a fuel such as uranium, maybe plutonium, and it will break up into smaller nuclei. It'll lose a little bit of mass in the process and give off energy. Then there's nuclear fusion, which is the opposite of that. Fusion is the process wherein two small nuclei stick together. They fuse together to make a larger one. This is what happens inside the sun and inside all stars. And so as we talk about the sun, and in the next unit when we talk about stars, the nuclear process that takes place is fusion. You look at these two protons that are coming at each other. Remember, they repel each other. At low speeds, the electromagnetic repulsion prevents the collision of nuclei. However, in a star, in the core of a star, high temperatures enable nuclear fusion to happen. So what happens is, in the core of a star where temperatures are very, very high, and that means that these nuclei are moving very fast, they will repel each other. However, they're coming at each other too fast to slow down and turn around in time. And so if they get close enough together, the nuclear strong force will bind them together. And remember from a previous chapter, the nuclear strong force overcomes the electrical repulsion. but it only acts at very short distances, like about the size of an atomic nucleus. So the nuclear strong force binds the protons together at very close distances. The strong force is the only force in nature that can overcome the electric repulsion between two positively charged nuclei. So inside the sun, it's a bit more complex than this, but this chart gives you the gist of it. You have 4 protons that fuse together. Now, they just don't come together as 4 protons and become a mass of 4 protons. Rather, they become a mass of 2 protons and 2 neutrons. So there's some other changes that go on. But essentially, 4 protons come together to make one helium-4 nucleus. Now, notice if you look at the picture, 4 protons designated by the letter P right there. But notice the caption down below, 4 hydrogen-1 nuclei. And I want you to remember that a hydrogen-1 nucleus is a proton. Hydrogen-1 means that, hydrogen means it has 1 proton. If it's hydrogen-1, it only has 1 nucleon, so no neutrons, just a proton. And so a hydrogen-1 nucleus is a proton. They come together and make helium-4 plus energy. The sun releases energy by fusing 4 hydrogen nuclei into 1 helium nucleus. Test yourself. The strong force is the only force in nature that can overcome the electric repulsion between, and what are the choices here? And it's good to have a skill that when doing a multiple choice test to get rid of, to eliminate the obvious wrong answers. So let's think through each of these. A proton and an electron. Well, protons are positive, electrons are negative. They are opposite charges. Remember, opposites attract. And so answer A doesn't make any sense because there is no repulsion before them. In fact, they attract each other. So let's eliminate answer A. Answer B, remember, neutrons are neutral. And so they have no electric attraction or repulsion. We can eliminate B. We can also eliminate D because, again, neutral particles such as neutrons don't have attraction or repulsion. So the only answer that makes sense here is C, 2 positively charged nuclei. I said a few minutes ago that it's a bit more complex than 4 protons coming together to make helium. Here it is, the full process. It's called the proton-proton chain. I don't expect you to memorize every step along the way. However, it's good to have seen it once to know that there are several processes that happen. So let me take you through it right here, through the proton-proton chain. Let's start at the top. 2 protons inside the core of the sun. They fuse together to make a proton and a neutron. Now let's think what that is. It's got 1 proton, so it's hydrogen, but it has a mass of 2, and that makes it hydrogen 2, otherwise known as deuterium. So 2 protons fuse to make a deuterium nucleus. And it kicks off these little particles. Let's go over to the key at the right. The little gray one is called a neutrino, and the little pink one is called a positron. So we've got this deuterium. Let's go to step 2. The deuterium nucleus and a proton fuse to make a nucleus of helium-3. And in the process, they kick off this energy. So this energy, this gamma ray, ultimately will be the light, the heat, the energy that we get from the sun. And you see the result when you combine the deuterium nucleus with 1 proton. Now you've got 2 protons and a neutron, and that is helium-3. Now, somewhere nearby in the core of the sun, the same process has happened, a duplicate process, 2 protons. They come together to make deuterium. Another proton comes in, fuses with the deuterium, gives off gamma ray energy, and you have another helium-3. So now by the end of step 2, you have 2 helium-3 nuclei. They fuse together. And in the process of fusing together, they kick off two protons. And this is always what happens during the process. Two protons get kicked off, and you're left with this helium-4 nucleus that's otherwise known as an alpha particle, the helium-4 nucleus. Now, swimming around in the core of the sun are also electrons, but you notice that the electrons don't play any part in the nuclear process. So let's look at what went into this, and we can make sense of this pink box that says overall reaction. Let's look at what went into it. A proton, that's 2, 3, 4, 5, 6. 6 protons went into all of this. 2 protons got kicked out. And so the net is that 4 protons went into it. And so now you go to the pink box for the overall reaction. And this is the part I do want you to know. 4 protons, otherwise known as hydrogen 1 nuclei, they came together, and what came out of it was energy, so that's the gamma rays, a bunch of little particles, some neutrinos and positrons, and a helium-4 nucleus. So this is the proton-proton chain, which is what creates the light and the energy that we get from the sun. Again, the overall reaction, what goes in is 4 protons or hydrogen nuclei. What comes out is a helium-4 nucleus, 2 gamma rays, 2 positrons, 2 neutrinos. The net result also is that it has lost mass. If you count up the mass of 4 protons, what went into it, and then count up the mass of a helium-4 nucleus, the 2 gamma rays, which don't have mass, positrons, and neutrinos, it loses a little bit of mass. It's about 0.7% lower. And by Einstein's equation, E equals mc squared, this leads to the energy that's created. Test yourself. Describe the overall process for the proton-proton chain. Now, 2 of these we should be able to eliminate fairly quickly. There are no molecules inside the core of the sun. It is way too hot for molecules. So we're just going to eliminate answers A and C that have water and oxygen molecules for answer A. And there it is, answer B. 4 protons become helium plus energy. And yes, there are those other little particles, the neutrinos and positrons, but those are little tiny particles, and often we're not going to count those. The big things that come out. 4 protons go to make helium plus energy. Let's talk about the solar thermostat. A thermostat is a very neat device. I'm talking about a thermostat in a house, in a building, where if it's getting too cold, maybe in the winter time, there are processes inside a thermostat that serve to kick on the heater, and it warms up the house until it gets too warm, and then the thermostat shuts off, so it doesn't get very warm. And in the summertime, you have an air conditioning in a house with the thermostat where it's too warm in the house, so there's a process that recognizes that it's too warm, so it kicks on the air conditioning and makes it cool until it gets cool enough, and then it kicks the air conditioner off, and it'll warm up again, and then kick the air conditioner back on again. That's what a thermostat does. The sun is this amazingly designed object that has a thermostat in it. So let's take a look at this, the solar thermostat, gravitational equilibrium. It says here a slight drop in core temperature. So what if it's getting too cool? Kind of like our house in the winter time, it's getting too cool and we expect the heater to kick on automatically. So if there is a slight drop in the core temperature, it leads to a large decrease in the fusion rate. So not as much fusion going on, and that lowers the core pressure. Remember, pressure, look at those red arrows, pressure is what pushes out against gravity, and there needs to be that gravitational equilibrium. So now there's lower core pressure because there's less fusion. And that means gravity is going to crush the core in more. So it causes the core to contract and heat up, thereby restoring the fusion rate to normal. So if there's a tendency, for whatever reason, if inside the core of the sun it gets a little too cool, that process will happen. The decline in the core temperature causes the fusion rate to drop, so the core contracts, and then it heats up again. Now, on the other hand, a slight rise in core temperature is going to lead to a large increase in the fusion rate. And that raises the core pressure. Notice the red arrows, they're going to push out against gravity, causing the core to expand and cool down, thereby restoring the fusion rate to normal. So a rise in core temperature causes the fusion rate to rise, so the core expands and cools down. And this is wonderful for us because it means we have a star, the star that gives us heat, that gives us light, the sun, and it has internal mechanisms that maintain equilibrium, that maintain a relatively constant brightness, relatively constant heat. And we need that for life on Earth. Now I want to look at how the energy from fusion gets out of the sun. It is not a straight path from the core out to the photosphere and beyond, as this picture implies. Energy gradually leaks out of the radiation zone in the form of randomly bouncing photons. And so you think it started in the core, and then it moves out to the radiation zone and then out beyond. This is what physicists call a random walk. Sometimes it's called a drunk man's walk, but I want you to look at the picture. Notice it's not a straight line outward. It's bouncing all around. The photons are bouncing all around between the charged nuclei and the electrons, and there is a general outward tendency, so it's not completely random, but a general outward tendency from the pressure to eventually make it out. But it takes between 100,000 and 1,000,000 years for a photon to travel from the core to the photosphere. Now, once it breaks free of the photosphere, it only takes a little more than 8 minutes to travel through empty space to get to us, but maybe as much as 1,000,000 years to get out of the sun. Here we have a diagram of the convection zone. Remember, that's the region right above the radiation zone. This diagram shows convection beneath the sun's surface. Hot gas, shown by the light yellow arrows, rises. It gets up to the top, and then it cools off and then sinks back down. So the cooler gas, shown by the black arrows, descends around it. So you have constantly the gas, really plasma, going up and down and up and down, and it's very turbulent. It isn't as nice and symmetric as these arrows imply, but very turbulent because you have gas crashing into each other, these particles, some going up, some going down, and it's very turbulent. So bright spots appear on the sun's surface where hot gas is rising, and then the gas sinks after it has cooled off. So this is the region known as the convection zone. Here's a picture of the surface of the sun, and the bright spot is hot gas rising, and the dark areas between the bright splotches are cooler gas sinking. The bright spots, each about 1,000 kilometers, about 600 miles across, correspond to the rising plumes of hot gas. Here you can see a scale. Here's the United States, which is about 3,000 miles across in comparison to those regions of hot gas and cool gas. And here is some video, short video of the surface of the sun. Now I want to get into how we learn about the sun's interior. I've been teaching you a lot in this chapter about what's inside the sun, but how do we know what's inside the sun? We learn about the sun's interior by mathematical modeling using known laws of physics. The more we learn about the sun's exterior, the more data we have for our mathematical models. So we learn a lot about its exterior. We can see what's going on the surface. We understand the temperature, the pressure, the fluid dynamics going on, the electromagnetism, and we have known laws of physics. And so we can use computer models, or we call them mathematical models, to come up with what exactly is going on at the center of the sun that would cause the what we see on the exterior. One project that has helped immensely with learning about the sun is SOHO, the Solar and Heliospheric Observatory. Here you can see it gets images and data from the sun and then beams it back to various locations on Earth. SOHO studies the internal structure of the sun, its outer atmosphere and solar winds, and the stream of ionized gas that is constantly blowing outward through the solar system. In this video, what have we learned? How does nuclear fusion occur in the sun? The core's extreme temperature, remember that's about 15 million Kelvin, and density are just right for nuclear fusion of hydrogen to helium through the proton-proton chain. Gravitational equilibrium acts as a thermostat to regulate the core temperature because fusion rate is very sensitive to temperature. How does the energy from fusion get out of the sun? Randomly bouncing photons carry energy through the radiation zone, and the rising of hot plasma carries energy through the convection zone to the photosphere. That is it for part 2 of chapter 14. Have a great day.